This is section 15.10, analyzing a proton NMR spectrum. So in this section, they have a really nice way to systematically go through and find out what a spectrum may be as far as molecular structure. And this is how I recommend you go about solving these as well. By first starting with the calculation of the hydrogen deficiency index, so you can know how many rings and or double bonds you have. For instance, as we see here in this little example, a benzene ring has an HDI of 4 because it is one ring plus 3 double bonds to give you an HDI of 4 overall. Next, once you find the number of the HDI and you have the molecular formula, consider the number of signals and integrations given for each signal, because these give you clues about the symmetry of the compound and the number of protons that are present for each type of signal. Next, look at each chemical shift, the integration, and the multiplicity, and draw molecular fragments that are associated with these signals. Once you've done that, assemble the fragments into a molecular structure. And once you've assembled them, verify that the proposed structure is consistent with all the spectral data. 5 easy steps to figuring out what a structure might be from its NMR spectrum. So a nice little example that is given in your book is shown here, where you have this relatively complicated looking spectrum, but becomes sort of simpler. First, for the HDI index, C9H10O. C9 should be H20, actually. So we have a hydrogen deficiency index of 5 after doing all of the math. I'll leave it to you to confirming that the answer should be 5, but just so you are aware, the O doesn't count due to our deficiency index rules, and I believe you'll find that 5 is indeed the correct answer. Next, let's have a look at the integration of these molecules, since we know that HDI should be 5. 5 tells us that there is likely maybe 1 or 2 rings, maybe there's a benzene ring and another double bond. Let's see. So in our integration values, we have 10, 50, and 2 20s. So what I recommend you do is to round them down or round them to the nearest whole divising, or first divide by the smallest number. Here it's 10. So that would mean that this is actually 1, what looks like 5.1, around 5.1, and around 2.1. So that means that you can round down those numbers to 5, and both of these being 2. And you know that there should be 1 proton, 5 protons, 2, and 2, for a total of 10. And the good news is we should have 10 protons. So now that we know our integrations, let's have a look at the shifts. So these 2 shifts are around 3 ppm and are indicative of maybe some alkyl groups that are near a mildly withdrawing functional group, maybe like something mildly withdrawing, something that has a little bit of polarity, but not much, because these protons are shielded relative to a normal alkane position. Next, we have this complicated looking signal around 7.2, and this is indicative of a benzene ring, especially by the fact that it has an integration of 5. We would expect that this would be a monosubstituted benzene ring. And then this signal here, a very sharp 1 proton signal near 10, is indicative of what's called an aldehyde. So let's go to the notebook and we can draw these things out like we just were saying. Okay. So what we have is the signals around 3, the signals around 3 ppm, some kind of alkane, the signals around 7, probably some kind of monosubstituted benzene, and the signal around 10 ppm was a signal of an aldehyde. And I'm using these squiggly lines to show that they have some connections here, and that's our fragment. So going back to this alkane one, remember that there were two triplets right next to each other, which tells us that likely that these are two CH2 groups bonded next to each other. And it's likely that there are two different groups bound to each carbon, both with different polarities. That would give us the overall 4 integration that we observed. So all that's left to do is to try to connect these in some way. And luckily, it seems like there's only really one way to draw these that would connect these two pieces. It looks like we would have something that would be, here's our benzene ring, and we'll connect that to our two alkane functional groups there. And then last, we just need our aldehyde. Oops, I'll just draw the regular hydrogen there. There we are. Okay, so then if we go back to the book and we have a look at to see what the expected structure should be after our little after our solving, we see that we indeed got the structure correct. So this is a good systematic way to go about solving proton NMR spectra, and this is section 15.10.